So last class we started our discussion on efficiency of a transformer, and we have discussed that the efficiency equation is the voltage output by voltage output plus losses. So the equation in the numerator V2 I2 cos theta 2 is under the condition of full load, where the iron loss and copper loss are also the full load losses. Iron loss being the constant losses will remain same irrespective of the load condition, whereas the copper loss will depend upon the load condition. So if we consider that X is the percentage of the loading, then the equation will change into two forms. First, the output will change into X into output, that is the full load output is multiplied with the X percentage of the loading. Iron loss will remain the same and the copper loss will be proportional to X square times the copper loss under the full load condition. So we know that the copper loss under the full load condition will be I2 square into RT, that is the total resistance referred from one side to the other. Here we have taken 2, so it means it is referred to the secondary side. If we take I1 square into R2 RT, it means the copper loss current is referred to the primary side and all the resistances are there in the primary side of the transformer. This copper loss is taken under the condition that this is the full load copper loss. So whenever you have X percentage of the loading, you have to take X square times the copper loss under the full load condition. So at any other loading condition, you can determine the efficiency of the transformer provided you know the efficiency under the full load condition. So if you know under the full load condition what are the losses, iron loss and copper loss, it will be easy to determine the efficiency of the transformer at different loading condition. So this we have discussed till last class, so we'll start our discussion ahead. So the first question is when the efficiency will be maximum, or the condition for the maximum efficiency. So the equation of the efficiency we write in this manner under the full load condition. So under the maximum efficiency condition, what we have to do is that if in the numerator and the denominator we divide the equation with I2, means in the numerator we divide it with I2 and in the denominator we divide the equation with I2, that is the current in the secondary winding, then we will be getting an equation in this manner where the numerator will be free from I2 and in the denominator your iron loss will be divided with I2 and the square term will vanish in the copper loss. We know that the V2 is constant. What is V2? V2 is basically the load voltage. So we know that the load voltage will be constant. So V2 in the load will be constant and only variable quantity will be the current, which is determined by the nature of the load. So if the load is resistive, inductive or capacitive, the current will vary. Thus, for a given power factor under the secondary load condition cos phi 2, the efficiency will depends upon the current I2. So the condition that efficiency is depending upon the current I2. So in order to determine the condition for maximum efficiency, what you have to do is that the equation of the maximum efficiency equation you have to differentiate with respect to I2 and then equate with 0. So if we differentiate the energy efficiency equation with respect to the secondary current and equate with 0, then a condition will be achieved that Pi is equal to I2 square into R2 RT. So this condition suggests that the iron loss is equal to copper loss. So iron loss, which is a constant loss and it doesn't depend upon the load condition, whereas the copper loss will depend upon the load. But here for the maximum efficiency condition, so the efficiency will be maximum under the condition that iron loss is equal to copper loss, or what we can say that the constant loss is equal to the variable loss. So value of output current corresponding to the maximum efficiency. So when you are connecting a load on the secondary side, V2 is constant and the current I2 is flowing, and we want an efficiency to be maximum. So what is this current I2? So in order to determine the secondary current under the maximum efficiency condition, we have to use the condition that iron loss is equal to copper loss. So from here we can find out that the secondary current or the load current is basically under root the iron loss divided by the total resistance. So here we are using RT. So RT means if you are calculating on the secondary side, so it will be R1 dash plus R2. So the current output current at the maximum efficiency condition, you have to remember it will be under root iron loss divided by RT, and the condition of the maximum efficiency is iron loss is equal to copper loss. Now, as I said that the iron loss will be a constant loss, that is iron loss will not depend upon the losses, and if X is the fraction of the full load kVA rating of a transformer for which the maximum efficiency has occurred, then the copper loss will be X square plus PC, PC being the full load copper loss. So this is the equation number 1 and this is equation number 2. So again I'm saying iron loss is a constant loss, it will not depend upon the load. Copper loss will depend upon what fraction of the loading is there and what is the full load copper loss. So this is full load condition, what is the copper loss, you multiplied with X square, that you will get the copper loss under any other loading condition. Now again, for maximum efficiency condition, you will be having the iron loss is equal to the copper loss at any loading condition. So iron loss will be X square times the copper loss. So this is your third equation. From here you can find out what is the loading on the transformer. So loading on the transformer will be under root iron loss divided by copper loss. So this is the loading on the transformer when you need to find the efficiency to be maximum. So what is the loading on the transformer for efficiency to be maximum is under root iron loss by copper loss. And the output kVA corresponding to the maximum efficiency, then what will be then the output efficiency? So when your efficiency is maximum, then output kVA is equal to the kVA under the full load condition multiplied with your X. So this is your X, which is the loading on the transformer, and this is kVA under the full load condition. So your efficiency maximum condition, the output kVA will be the kVA under the full load condition multiplied with the loading on the transformer. So this discussion was corresponding to the efficiency of the transformer. You have to remember few points. First, the efficiency will be maximum under the condition that iron loss is equal to copper loss. So iron loss is equal to copper loss. So iron loss being the constant loss irrespective of the loading condition, and copper loss it depends upon the loading condition. So this is under the full load condition. Iron loss is equal to copper loss. If at any other load you want to find, then you have to multiply it with X square. So X square into PC, PC being the full load copper loss, and X is the percentage of the loading. Now, what is the secondary current corresponding to the maximum efficiency? So in that case, it will be iron loss divided by the total resistance in the circuit. So if you are trying to find the resistance from the secondary circuit or the primary circuit, you can do as usual. So here you are taking I2. So here you have to determine RT2. So on the secondary side, you have to determine. So these equations will be helpful in solving the numerical on the efficiency of the transformer. Now we have defined the efficiency. There is one more term which is known as all-day efficiency. So we have defined efficiency is the power output by power input. But here we are taking power term. So in all-day efficiency, instead of power, we will take energy. So when energy will be there, then here all-day efficiency will be calculated. So let us see what is all-day efficiency. So power transformer at any generating station and distribution transformer in the distribution substation, we will calculate the all-day efficiency. So in the generating station, whatever the transformer is there, that is known as the power transformer. In the substation where the power is distributed, that is known as the distribution transformer. So we have to calculate the all-day efficiency of the transformer. So power transformer are switched in and out of the circuit depending upon the load to be handled. So this load is basically the consumer. So when the consumer is taking the load, then what is happening? The power transformer is switching in and out of the circuit. Distribution transformer is never switched off. So distribution transformer is never switched off and remain irrespective of the load condition. So when the load in the system changes, it is the power transformer which is taking the energy or the voltage from the generator, and the voltage is stepped up. But it can be switched in or switched out depending upon the load condition. Distribution transformer is never switched off, and irrespective of the load condition, it has to operate. So in such cases, the constant loss continues to be dissipated. So constant loss is basically the iron loss. So this depends upon the magnetization of the core. So core magnetization will remain always when the transformer is under the on condition. So even your load is 0. So even your I2 is 0 when your load is 0. Then also your iron loss will be there, because iron loss depends upon the voltage V1. So iron loss will be continues to be there even the transformer is not drawing any load. So concept of energy based efficiency is known as all day efficiency. So here whenever we were defining the efficiency, we define in terms of the power. So power output by power input is the normal efficiency, whereas when energy is there to calculate the efficiency, then it is known as all day efficiency. So all day efficiency generally suggests that how the transformer is being utilized. So the definition of all day efficiency, how do we define it? So instead of power, we will use energy now. And what is the unit of energy? The energy unit will be kilowatt hour. So output energy in unit kilowatt hour in a particular day. Okay, so in a day you will be having 24 hours. So in 24 hours time, what is the output energy in kilowatt divided by the input energy in kilowatt for that particular day multiplied with 100, you will get the all day efficiency of a particular distribution transformer. So here, instead of using the power output by power input, which we have determined the efficiency of any transformer, when we need to find the all day efficiency, we will go for energy output by energy input, and the unit has to be always kilowatt hour, and that is under 24 hours time, that is one day. So all day efficiency is always calculated in a particular day, so the name suggests all day. So one day, okay, one day means 24 hours. So here the same equation can be again written as in terms of the losses, what is output energy by output energy plus energy spent for the total losses into 100. So similarly to power equation, where you define power output by power input, and you can write the power input is equal to power output plus losses. So here also you can write energy output plus the energy spent for the total losses. So this is all day efficiency. So whenever in the numerical you have been asked to determine the efficiency, you have to determine in terms of power output by power input. When you are asked to determine the all day efficiency, you have to convert the power in terms of energy in kilowatt hour in a particular day, and then determine the all day efficiency. So the next topic that we are going to take is basically what is an auto transformer and its functioning. So single phase transformer, two winding transformer is over. We will discuss our new topic as auto transformer. So auto transformer is basically known as the variac, right? So variable AC is known as the variac, where you can slowly vary the output voltage of the transformer. So irrespective of the loading on the transformer, you can slowly vary the output voltage, which is not possible in case of the single phase two winding transformer. So in the two winding transformer in single phase, your output voltage V2 will depend upon the input voltage V1, and you can't control this voltage V2. So there is no controlling of this voltage V2. So this is a two winding transformer iron core single phase. Whereas in the varia or the auto transformer, which is a variable AC transformer, you can control this voltage V2. So in order to control this voltage, that is known as the auto transformer. So this is the auto transformer that we have been using in the lab. So here also you will be having a primary circuit and a secondary circuit. So primary circuit will be given the supply voltage. So here the V1, which is the supply voltage, will be given at these two particular nodes. So one is the AC supply, whatever is there. So you can give an AC supply here. So this will be V1, and your V2 will be tapped by revolving this knob. So this knob can be revolved in this direction to control the level of the voltage V2. Now the question is, how do we control this voltage V2 and to get a required amount of the voltage? So let us discuss that point in detail. So transformer with one winding we have discussed. Right? Sorry, the transformer with two winding we have discussed, and in auto transformer you will be having one winding only. So here, if you remember, in the two winding transformer we have two winding. So two winding means you have a primary winding and secondary winding, and primary winding is connected to the supply and secondary winding is connected to the output. So here we will be having one winding which will be used for V1 and V2. So both V1 and V2 will be the part of the one winding only. So part of the winding is common to both primary and secondary. So as one winding is involved to control V1 and V2, so part of the winding is common to both the primary and the secondary circuit. So when we will see the architecture or the circuit of the auto transformer, you will understand how this part plays an important role to control both the primary circuit and the secondary circuit. Now, in a two winding transformer, there is an electrical isolation. So, whenever you will be having a core, and this is your primary winding and this is your secondary winding. So, if you see, the primary winding and secondary winding are not electrically connected, they are isolated. In a two winding transformer, your primary winding and secondary winding are isolated, whereas no electrical isolation will be there in the no electrical isolation will be there in your auto transformer. So here electrical isolation is there, and this is part of the magnetic circuit. So this conductor is not in connection with the other conductor. Okay, but here, since one winding is there and that to be form a part of the primary winding and the secondary winding, there will be a physical connection between the winding. Theory and operation remains the similar. So there is no change in the theory or operation. So whatever you have understood for a two winding transformer, similar operation will be there here, only the connection will change. Because of one winding, user less copper and hence cheaper. So if one winding is there, obviously less copper will be utilized and hence it will be cheaper. So auto transformer will be cheaper compared to the two winding transformer because less copper is involved. It is used where transformation ratio varies little from unity. So if you remember, K is equal to N2 by N1. So number of turns in the secondary circuit by number of turns in the primary circuit is known as the transformation ratio. So this transformation ratio can be anything in case of a two winding transformer because it will depend upon the number of turns. However, in auto transformer we will use where it is close to unity. So where the number of turns on the secondary winding and number of turns in the primary winding are such that it will be close to unity, means it will cancel out each other. There only auto transformer will be used. Okay, so now as V2 we are controlling slowly, so this V2 is being controlled by changing the number of turns in N2. So by changing the number of turns in the secondary winding N2, you can control the secondary voltage V2. So just to remember, in the auto transformer you will be having one winding and both winding will be physically connected, so electrical isolation will not be there as in a two winding transformer. And here the part of the winding will be from the supply voltage and part of the winding will be secondary voltage. So if you see this circuit of an auto transformer, there is only one winding. So this winding is one winding is there, which is an auto transformer winding. The part of the winding is forming the primary voltage. So this part of the winding which we are tapping with the number of turns in NP, that is the number of turns in the primary winding, we can give the supply voltage. So this is your input V1. Whereas if we are tapping at different points N3, N2, N1, N1, N2 and N3 are basically the tappings that are available in the other part of the winding. So if you are tapping in another part of the winding, you can get a variable voltage on the secondary of the transformer. So VS1, VS2 and VS3 are the variable voltage on the secondary of the transformer V2. So unlike a two winding transformer, here you can get a variable voltage on the secondary of the transformer. So let us discuss the auto transformer into two different mode of connection. One is known as the step down auto transformer and another one is step up auto transformer. So if you remember, in a two winding transformer you will be having two winding, and this is your primary voltage V1 and this is your secondary voltage V2. You are having N1 number of turns and N2 number of turns. So here in step down transformer, your your N1 will be more than N2, whereas V1 will be more than V2. In step up transformer, your V2 will be more than V1 and N2 will be more than N1. So same thing we are trying to get in auto transformer also, and we are not using any two winding. What we are using? We are using only one winding. So how to use one winding to get a step down and step up voltage? So here you can observe that only one winding is there. Now if the total turns, so this total turns of the winding is given the supply voltage which is forming the primary winding, and a part of the winding is taken from the secondary to connect with the load, then this is known as the step down auto transformer. Because here if you see, the entire winding is forming the primary side, whereas the part of the winding, this part of the winding is only in the secondary circuit. So obviously your N1 is greater than N2. So this is your N2, whereas this is your N1. So this is known as step down auto transformer. Whereas in a step up auto transformer, if you see, the entire winding is taken outside of the load. So the number of turns in N2 is more than the number of turns in N1, which is the primary winding. So primary winding is only this part of the circuit, whereas the secondary winding is entire winding. So here N2 is more than N1, hence it is known as the step up auto transformer. So we will just try to understand the flow of the current and the voltage, taking an example of step down auto transformer. So we will take an example of step down. So step down auto transformer. So here only one winding is there. So this is your one winding. Now V1 is the supply voltage. Since it is a step down auto transformer, your N2 will be less than N1, right? N2 will be less than N1. So if we take N1 is the total number of turns, if we take N1 as the total number of turns in the circuit. So if N1 is the total number of turns in the circuit which is forming a part of V1. So N1 is forming a part of V1, and a tapping is provided at some point in the winding, and then this winding is being divided into two parts. So one is N1 minus N2 and another is N2. So what we have, N1 is broke down into two parts. So one is N1 minus N2 and another is N2. So if you add both, then it will be N1 only. So the part of N2 is being tapped in the load. So part of N2 is being tapped in the load. So whatever the current is being drawn in the primary circuit I1, now here if you see at this point, if you apply a Kirchhoff's current law, then I2 being the secondary current which is flowing through the load. So I1 is the primary current and I2 is the secondary current. I1 is associated with the source, I2 is associated with the load. Then if we apply a Kirchhoff's current law at this particular point, then you will be getting a current I2 minus I1 flowing in this direction. Because in this direction you have I1 and in this direction you will be having I2 minus I1, whereas I2 will be flowing in this direction. So at this particular point, if you apply a Kirchhoff's current law where the current entering is I1, here current entering is I2 minus I1, whereas I2 is the current leaving here. So I1 is the current of the primary which is connected to the source. I2 is the secondary current which is connected with the load. Now entire this part of the circuit is forming the N1 number of turns, whereas this part of the circuit is forming N2 number of turns, and this is grounded. So in this way, having one winding alone, you can have the voltage step down from V1 to V2 to form a step down auto transformer. Now, as we know that in auto transformer there is saving of copper. So due to saving of copper, the cost or the price of the auto transformer is less compared to the two winding transformer. So that derivation we are going to do, and how much saving of copper can be possible when we take the two winding transformer as the reference. So let us derive that. So the volume or the weight, you know, it is proportional to the length and area of cross section. So volume is proportional to the length into area, right? So this is the length and this is the area. Whereas the length of the conductor is proportional to the number of turns. Length of the conductor is proportional to the number of turns, and cross section depends on current. So cross section area of the conductor will depends on the current, right? So entire cross section area, this is your conductor, so this is your cross sectional area where the current will flow. Therefore, the weight is the product of current and number of turns. So the conclusion is the weight which we are going to determine the volume is the product of the current and the number of turns. So number of turns into current is basically the volume or the weight of the conductor, right? Weight of the conductor. So if we determine the weight of the conductor in section AC. So if you remember the previous diagram that we have drawn, so I'll draw it again. So this is your entire winding of the transformer, and from here you are going to do the tapping, right? So if you see here, we have taken a point C, and here we have taken A, and this is your B. So let us draw again. So this is your A, this is your C, and this is your point B. Sorry, this is your C and this is your B. Okay, so what is the weight of the copper in section AC? So in this part of the circuit, that is AC part of the circuit, the number of turns was N1 minus N2 and the current was I1, because I1 was the current flowing in this side and this number of turns was N1 minus N2. So the product of number of turns into current will give the weight of the copper in a particular section. So for AC we have determined weight of copper in section BC. So this side your number of turns is N2 and the current flowing is I2 minus I1. So N2 product with I2 minus I1 is the weight of the copper in section BC. So what is the total weight of copper then? So total weight of the copper will be then summation of the first quantity plus the second quantity. So N1 minus N2 into I1 plus N2 into I2 minus I1. This is coming from the first AC part. This is coming from the BC part. Now this is what we have discussed for an auto transformer. This is for the auto transformer. We have discussed what is the total weight of the copper. Now let us discuss if the transformer is a two winding transformer, then what could have happened. For a two winding transformer, so this is your first winding and this is your second winding. Here the number of turns is N1, here the number of turns is N2. The current flowing is I1 and the current flowing here is I2. So obviously the total weight of the copper would be proportional to N1 I1 plus N2 I2, because this part is not connected with this part. So N1 I1 plus N2 I2 is the total weight of the copper for a two winding transformer. Now what is, if you take the ratio of weight of copper in auto transformer by weight of copper in an ordinary two winding transformer, what we are going to get? So basically weight of copper in auto transformer we have derived N1 minus N2 into I1 plus N2 I2 minus I1. So we have derived by the two quantities, one is AC and another is BC. And weight of copper in a two winding transformer is straightforward N1 I1 plus N2 I2. So if we take N1 by N2 or N2 by N1 as the transformation ratio, this equation when we will reduce into smaller format, we will get 1 minus K, because we know that the value of K is equal to N2 by N1 is equal to I1 by I2. So this concept we are going to use it here and do appropriate manipulations, which I have not shown it here. You can do as an homework part. So you will get 1 minus K. So K being the transformation ratio of the network. So the weight of the copper in auto transformer is 1 minus K into weight of the copper in ordinary transformer. So this ratio, if we take this to be auto transformer divided by the ordinary transformer, so what we are getting, weight of copper in auto transformer is equal to 1 minus K into weight of copper in ordinary two winding transformer. So from this equation you can easily visualize, because the value of K will be always less than 1. So obviously the auto transformer WA weight will be less than the two winding transformer always. So that will produce the saving of copper. Okay, so please remember this equation. Weight of the auto transformer copper is equal to 1 minus K, where K is the transformation ratio of the two winding transformer, multiplied with the weight of the copper in ordinary two winding transformer. So what is the saving then? So the saving of copper is basically weight of the two winding transformer minus auto transformer, right? Then the auto transformer copper is equal to 1 minus K into the two winding auto two winding transformer. So basically the saving that you are getting in copper is equal to K times W naught. So you have to remember two equations. One is weight of auto transformer copper is equal to 1 minus K, that is transformation ratio, into the two winding transformer, and the saving of copper will be then K times W naught. So this is the saving of the copper. So we have understood the importance of an auto transformer advantage than the two winding transformer is that there will be saving of copper. So saving will increase as K approaches unity. So saving will be maximum when the value of K is 1. So value of K is 1, then you will be having saving to be more. That is the reason in auto transformer we are keeping the value of the transformation ratio close to 1. Okay. Now in two winding transformer where you have the two winding, these two windings 1 and 2 are not connected with each other. So the entire energy from this part of the circuit to here is transferred inductively. So there is inductive transformation of energy. Whereas in case of an auto transformer where you have only one winding, then energy from the first part to the second part, that is the primary to the secondary, is transferred both inductively as well as conductively, because this is an conduction. There is a conduction process. Two windings are connected to each other, so power will be transferred both inductively as well as conductively. So power transferred inductively is equal to the power input into 1 minus K, and rest of the power, that is the power conductively, it is transferred as input into K times. So these equations are very important when you try to solve any problem on auto transformer. So inductively power transferred is equal to power input into 1 minus K. Conductive transfer is equal to K times the input. So we have seen in an auto transformer what is the power transferred and what is the saving of the copper, and how the operation of the auto transformer is there in a single winding transformer depending upon the number of turns and the current. So let us look into the advantage of auto transformer, disadvantage and the application. So advantage of auto transformer is it is less costly, better regulation you can achieve, and low losses as compared to two winding transformer of the same rating. So these advantages of auto transformer is because the transformation ratio K is equal to 1, close to 1 we can say, that is transformation ratio will be close to 1. Second thing is that when transformation ratio is close to 1, what will happen? The V1 value will be normally equal to V2, right? So at a particular point of time when you are turning the voltage, so V1 is normally equal to V2, so you'll get better regulation. So under the no load condition and the full load condition, you will get better regulation, and less costly because you will be having K into W naught as the saving of the copper. Losses will be also less here because in a two winding transformer, if you remember, there is a core and both the winding are not physically connected to each other. So there is a loss here that is represented by the shunt parameter. So because of that losses, the two winding transformer will have more losses compared to an auto transformer. Disadvantage, if you see, so the secondary winding is not insulated from primary. So both primary winding and secondary winding are connected to each other. So there is no electrical isolation. So if a low supply voltage is used from a high voltage source, and if a break occurs in the secondary winding, then full primary voltage comes across the secondary terminal, which is dangerous to operator and the equipment. What is happening? Because the V1 is normally equal to V2, because the transformation ratio K is close to 1. What is happening? When you are giving a supply voltage, now if you are giving a supply voltage from a high voltage source, and since the two winding of the transformer are not electrically isolated to each other, so what will happen? Under an extreme condition or faulty condition, the entire voltage will be there in the secondary of the transformer, and that is very dangerous to the operator who is operating the equipment. This is the first disadvantage condition. Use only in limited places where a slight variation of the output voltage from input voltage is required. So the basic application of the auto transformer is limited, very limited. So where we required to control the voltage. So in order to control the voltage, we use auto transformer so that the voltage in V2 is slowly varied and we can control the voltage V2. So that we can understand from various applications that we are using. Even in the lab we use this variant, right? So application of auto transformer, let us see. So use as a starter to give 50 to 60% of the full voltage to the stator of a squirrel cage induction motor during starting. So generally any AC motor, whether it is an induction motor or you have a synchronous motor, you will be requiring to slowly vary the voltage. So that will be used as a starter. So if you remember in a DC, we were using a starter which is we are changing the resistance. So when we are changing the resistance, we are controlling the input current. Here in AC application, in order to control the voltage, we will use a auto transformer. So this is basically in terms of induction motor. Second, used to give a small boost to a distribution cable to correct the voltage drop. So this voltage drop is basically due to the inductor. So when inductor is there in the distribution cable, then what happens? There is a voltage drop due to the loss. So the auto transformer will boost the voltage. It is used as a voltage regulator because you are controlling the voltage by turning the knob. It is used as a voltage regulator. It is used in power transmission and distribution system and also in audio system and railways. So application in railways, audio system or transmission and distribution system, everywhere auto transformer is being used where you can control the voltage. So today's lecture topic, the discussion was primarily focused on the efficiency of the transformer, and efficiency of the transformer was determined in terms of power output by power input, and what is the condition of maximum efficiency, what is the current corresponding to maximum efficiency, what is the loading when the maximum efficiency has occurred, that we have discussed. Then we have discussed the concept of all-day efficiency. So all-day efficiency requires you to find the energy of the output and the energy of the input in kilowatt hour for a particular day. There will not focus on the power, rather will focus on the energy. So all-day efficiency. Third, we have seen the construction of the auto transformer. Principle of operation remains the same. Only if we know the architecture or the circuit configuration of the auto transformer, we can calculate the voltage, we can calculate the current, knowing the number of turns on the primary side and the secondary side. We have calculated the saving of the copper in auto transformer and how the power is transferred inductively and capacitively. Now we have discussed the advantage, disadvantage and application. We will stop our discussion till here and then we'll focus on the next class.